This section is going to continue our work in chapter 1, looking at different types of functions. Specifically, we're going to look in the first part at polynomial functions, and then the second part rational functions. Okay, a polynomial function can be written as you can see up here, but I think that makes it look like it's worse than it really is. So when we're talking about a polynomial function, we're talking about something like this. So this would be an example of a polynomial functions. There's no denominators, no negative exponents, no fractional exponents, things of that nature. So just a basic function that we're working with. It could even be a quadratic function. A quadratic would be an example of a polynomial function. So you do need to know a couple things, like when we talk about leading coefficients. The leading coefficient is when your polynomial is in descending order based on the degrees, which this one is. This is going to be your leading coefficient. So the first coefficient, or the coefficient in front of what we call the term with the highest degree. Okay, so this would be a 4th degree polynomial. And so that's going to be, the coefficient in front of that is going to be considered our leading coefficient. Okay, the domain for a polynomial is very nice. It's a set of all real numbers, no restrictions. The range kind of depends on the degree that you're talking about. We'll look at that a little bit more later. So if we happen to have a constant function, so let's say our polynomial was just equal to 3, then it's not very interesting, but the degree of that would be 0, because there is, if you wanted to think of it as x to the 0 power, since that x is not really there, then that would be why it is a degree of 0. A linear function might look something like this. Okay, so this is to the 1st degree, and that would be a linear function, which would be a polynomial. And then quadratics are also polynomials, so that would be something like x squared minus 6x plus 3. So we have a square term, our degree would be 2 on this one. Okay, so a few things to kind of mention. If we have, when we're looking at the degrees, the shape of the polynomial graph is determined by whether the degree is odd or even. So if we have an odd degree polynomial, a couple of characteristics here. All odd degree polynomials are going to cross the x-axis at least one time. So generally when you're talking about an odd degree polynomial, you're talking about something that looks like this. So it goes and comes from opposite directions, and because of that, it's going to have to cross the x-axis at least one time. It might be that it crosses more times than that, but it will cross at least once. All odd degree polynomials with positive leading coefficients start negative. So like this one is starting down here at negative infinity, and it ends positive up here at positive infinity. So this would be one that has a positive leading coefficient. If I look at one like this one would have a negative leading coefficient, because this one starts at positive infinity and ends at negative infinity. So the leading coefficient and the degree are important as far as the shape of the polynomial. Okay, if we're talking about even degree polynomials, even degrees are always going to look either something like this or something like this, okay? And it may have more or less of these bumps along the way, but basically, if when we're talking about even degrees, some even polynomials never intersect the x-axis. So for instance, like this one, if the x-axis is something like this, well, it's never going to come down and touch there. Sometimes it will touch like this one, but it doesn't have to. So all even polynomials that start positive end positive, and that's the ones that have a positive leading coefficient. So like this one is starting at positive infinity and ending back up at positive infinity. So in other words, even degree polynomials come and go from the same direction. So this would be a positive leading coefficient. This would be when they have a negative leading coefficient. It's coming and going from negative infinity. Okay. All right, so graphing a polynomial of degree 1. I'm not going to spend a lot of time talking about the graphs. You can generate these on your calculator. Anytime you're given function notation, just remember you can go to like y1, y2, whatever, and put it in, and it's going to give you your graph. So this would be a first degree polynomial. It's just a line. So it does fit the characteristics we've talked about of coming and going from a different direction and crossing the x-axis at least one time. Okay, if we look at the graph for this one, this is a third degree polynomial with a positive leading coefficient. So that tells me an odd degree positive leading coefficient, the general shape of it is going to look something like this. Okay, and that's what we see here. So these other terms kind of affect how many turns. Okay, so let me say that a little plainer. These other terms will affect how many turns the actual graph has when we look at it. Okay, this one is, if we look at this, we've got a fifth degree polynomial, so another odd degree polynomial with a positive leading coefficient. So it's coming from negative infinity and it's going to positive infinity. It crosses the x-axis at least one time, and it has an odd degree, so we would expect that. One thing I want you to make note of is the number of turns. So this one turns 1, 2, 3, 4 times. So if you've got 4 turns, then that means that you could have up to a fifth degree polynomial. Okay, so looking at some even degree polynomials, this one you've got an even degree with a positive leading coefficient, so it's going to go and come from positive infinity with this, and this particular one does not touch the x-axis. Okay, this one is an even degree positive leading coefficient, so again it goes and comes from in positive infinity, and if we look at the number of turns, we've got 1, 2, 3 turns and on a fourth degree polynomial. So you can have as many as 3 turns. You can have as many as 1 less than the degree for the number of turns. Okay, this one we've got a sixth degree polynomial. So again, it goes and comes from positive infinity because it has a positive leading coefficient. We've got 1, 2, 3, 4, 5 terms on a sixth degree polynomial. It doesn't have to have that many, but it may have that many. All right, so kind of going through these. Each odd degree polynomial graph started negative and ended positive, basically, which was what we had expected. The ends of each odd degree polynomial moved in opposite directions, so they go and come from different directions. Each odd degree polynomial crossed the x-axis at least one time, so we did observe that. Each even degree polynomial started positive and ended positive because all the ones that we looked at actually had positive leading coefficients. And then some of the even degree polynomials crossed the x-axis and some others did not. And the ends of each even degree polynomial moved in the same direction. So the even degree polynomials go and come from the same direction. Okay, no graph crossed the x-axis more times than their degree. If we look back at some of these, like this one crossed 1, 2, 3, 4 times. So the number of times that it's going to touch the x-axis is always going to be less than the degree. Okay, so changes in direction are limited to 1 less than the degree, which is what we were talking about earlier. Okay, so for the following graphs, these are all polynomials. So for each graph, we want to tell whether the degree is odd or even and give the sign of the leading coefficient. And maybe even, let's talk about what the degree might potentially be. So this one's linear. It goes and comes from opposite directions. So we definitely have an odd degree, and since it's rising, going from a negative infinity to positive infinity, it's going to have a positive leading coefficient. And a linear function would have a degree of 1. This one goes and comes from the same direction, so this would be an even degree with a positive leading coefficient. and it turns 1, 2, 3 times, so it could potentially be a fourth degree polynomial. This one, if we look at it again, it goes and comes from the same direction, so it would be an even degree with a positive leading coefficient, and it only turns one time, so it might be a second degree polynomial. This one comes from negative infinity and goes to positive infinity, so it would be an odd polynomial, an odd degree polynomial. It has 1, 2, 3, 4 turns, so it might be as much as a fifth degree with that, or at least a fifth degree. And then if we look at whether it's a positive or a negative leading coefficient, this one goes from negative to positive, so it would be a positive leading coefficient. This one goes and comes from the same direction, so it's going to be an even degree, but because it's negative infinity that it's going and coming from, it's going to be a negative leading coefficient, and it turns 3 times, so it might be at least a fourth degree, or it would be at least a fourth degree polynomial. This one comes from infinity and goes to negative infinity, so that means it's going to be odd. It turns twice, so it would be at least a third degree polynomial, and it would have a negative leading coefficient. Some other characteristics of polynomials is they are continuous and smooth functions. So when I look at one like this would not be a polynomial because we have what's called a point of discontinuity, which basically is a break in the graph. We've got a jump here that occurs from one piece of the graph to the other, so it's not continuous and therefore not a polynomial. If we look at this one, I don't have to pick my pencil up at all, but it's not smooth. This is a sharp turn, a sharp corner, so anytime I have a sharp corner, then it's not going to be a polynomial. And then the last one here, if you follow this, there's no breaks in the graph, there's no sharp turns, no corners, so this would be an example of a polynomial.